Which one do you want me to do? Last one? So this, on this particular quiz, number 4, gave you the expression sine of 20 degrees, secant pi over 8, divided by cosine of 70 degrees, times cosecant 3 pi over 8, plus tan pi over 4, and I wanted you to evaluate or find the exact value of the expression. What is it? 2. Yes. Oh, yes. Why is it 2?
Because if you take the fraction apart, the sine and cosine are co-functions.
Yeah, so focus on each part here. Right? You have sine of 20, cosine of 20, and then you have secant of something and cosecant of something. Now, in order for these cofunctions to be equal, these have to be complements. Right? So you do have something to check to make sure that I'm not trying to trick you. Right? These guys are obviously the same because sine of 20 and cosine of 70, they're cofunctions and they have complementary angles. Right? So remember that was our idea or our identity about cofunctions. If you have two cofunctions and they have complementary angles, then they're the same. So sine of 20 degrees is equal to cosine of the complement. Now as far as secant and cosecant, secant of pi over 8 should equal cosecant of whatever you get when you take pi over 2 and subtract pi over 8. Right? Because that's how you find a complement, is you take 90 degrees, but since we're in radians, we're not going to use degrees. So you take pi over 2 radians and subtract pi over radians, and that'll give you the complement. But pi over 2, if you get a common denominator, is 4 pi over 8 minus pi over 8 is 3 pi over 8. So secant of pi over 8 is equal to cosecant of the complement angle, which is 3 pi over 8. So these are equal here, and these are equal. So the top of this fraction and the bottom of this fraction is equal, which means that the whole fraction equals 1. Right? This part right here is 1. And then tangent of pi over 4 is 1. Right? For that one, you might actually need one of your special triangles. Right? Pi over 4 is 45 degrees. So you know it's 1, 1, root 2. Tangent is opposite over adjacent. So tangent of pi over 4, opposite over adjacent, equals 1 over 1. So this part right here is also 1. So it's as easy as 1 plus 1. Depends on your test. Oh, the same one that I just used? So the first one gave you, number 1, gave you a right triangle with a theta, and then a B and an A, and then it told you that A is 7 and B is 25. And then it wanted you to find cotangent and secant and cosecant. So in order to find cotangent and secant and cosecant, you need this third side. How do you find this third side? Right, Pythagorean theorem. You got to be a little careful. I don't know why they use B. I got this from a test bank. I don't know why they use B for this side. That blew my mind.
Yeah,
it's like that.
But it's all right. We'll roll with it. We'll roll with it. All right. This is the adjacent. Or let's call this x. That'll be easier. So then if we do x squared plus 7 squared, it should equal 25 squared. So x squared plus 49 should equal 625. So you subtract the 49, and you get x squared equals 574, or 576, and then you square root, and it becomes 24. So this side is actually 24. So then you can go into all your definitions. Right? You know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. For your reciprocal function, secant, cosecant, and cotangent, you have to flip all of these. So secant, for example, is the reciprocal of cosine, so he's h over a, which will be 25 because that's the hypotenuse, over the adjacent side. This a stands for adjacent. So secant would be this over this. Cosecant, that's the one that matches up with sine, so this will be a hypotenuse over opposite, 25 over 7. And then cotangent, that matches up with tangent, so that'll be adjacent over opposite, 24 over 7.
And what was the correct answer on the test then?
On this particular test, looks like B. Or secant 25 over, yeah, B. On the other test, there's a similar problem with the answer with different numbers, and the answer will be different.
I cut the part.
Alright, so if you have questions, you can ask me after class. If you want to go over the quiz, feel free to stop up after class and we can talk about anything. Okay? But for now, since we're getting a little bit behind, let me just power through and get through the 6.3 stuff. We started last time talking about reference angles and defining trig functions for angles that are greater than 90. Okay, so I want to review a little bit about what a reference angle is and then the definition, and then get into the rest of the section. So start with this example. Find the reference angle for 15 pi over 4. So what's a reference angle? How do you figure it out? So a reference angle is the positive acute angle that has the x-axis as one of its sides and the terminal side of this angle as its other side. Okay. So I gave you a handy remark or theorem or formula or whatever you want down here about angles that have 4 in the denominator, radian angles that have 4 in the denominator, or 3 in the denominator, or 6 in the denominator. If you have a radian angle like this, where it has a 4 in the denominator, and I cannot reduce this, you know automatically the reference angle is going to be pi over 4. Why? As you're working the problems, and as you get used to this, you'll just be able to jump from here to here. But for now, for review, let's talk about why. Why is the reference angle for this guy pi over 4? Well, I would draw it. Okay. What does 15 pi over 4 look like? Where does it land? Yeah, so I would probably, because 15 is so much bigger than 4, I would turn this into a mixed number to make my life a little easier. Right, 4 goes into 15 3 times with a remainder of 3. So this is really 3 3/4 pi. So as you graph this, here's 1 pi, right? 1 pi is just a half rotation. 2 pi, another half rotation. 3 pi. And then from there you have to go 3/4 of pi. So you break this bottom pi into 3 separate quarters. 1, 2, 3, 4. So I break it into 4 quarters and I only go 3 of them. So I land here. So I went 1 pi with my half revolution, then I went 2 pi with another half revolution, then I went 3 pi with a third half revolution, and then I went 3/4 of pi by breaking it into quarters and going 3 of them. So this is where 15 pi over 4. And the reference angle is the angle that you make that is formed by the terminal side of theta and the x-axis. And it has to be a positive acute angle. So you see the x-axis and the terminal side of theta can form 2 angles. This bigger one and this smaller one. The reference angle is always the smaller one. So this right here is your reference. And now you can see that it's pi over 4 because we went 1 pi over 4, 2 pi over 4, 3 pi over 4, so we only have one more quarter left before we get back to the axis. So from the drawing, it's clear that there's a quarter pi right here. That's why my reference angle is pi. All right. Questions about that? All right, we talked about this. We talked about how we're going to start defining our trig functions. It's an extension of this idea of opposite over adjacent, opposite over hypotenuse, blah, blah, blah. So the way this definition worked is you took some angle theta. This is kind of the last thing we rushed through on Monday. If you take some angle theta, until you form a right triangle with theta, it's really hard to talk about the trig functions. And if this angle is bigger than 90 degrees, it's kind of hard to form a right triangle. So what this definition does is it gives you a consistent way to form a right triangle with theta. You just take the reference angle, which is always made with the terminal side of theta and the x-axis, and then you make that reference angle part the acute angle in a right triangle. And then, if you think about any point on that ray as xy, which isn't super crucial, but kind of what this lets you do if you think about a point as xy is it tells you that this distance here can be labeled x, and this distance here can be labeled y. This hypotenuse distance we normally label r, and we get it by taking the square root of x squared plus y squared. And from this, we can get all of our trig normal definitions that we were used to from last section. So what you want to keep in mind is that in relation to this reference angle here, y is the same as opposite, right? Because it's opposite from the reference angle. And x is the same as adjacent. It touches the reference. And r is the same as hypotenuse. So when we go in and give you these new definitions, we're going to use x, y, and r, but they're really just different names for the same thing. Like sine of theta will now be y over r. It's opposite over hypotenuse. Right, cosine x over r, and tangent is y over x. So for the rest of this section, what we're trying to do is get used to using these definitions, okay, when we have angles that are bigger than 90 degrees, bigger than pi over 2. I didn't write all of them up there. Right? I didn't bother writing cosecant, secant, and cotangent because you would just flip these. But theoretical questions, or any questions, I guess.
When you have r equals square root of x plus y.
X squared plus y squared, yeah.
What does that mean?
It means that r equals the square root of x squared plus y squared. So like if I have it, like I'll have to have an x and a y to make this make sense. But if I have like x equals 2 and y equals 3, then I could find this side by doing r equals 2 squared plus 3 squared square root.
Wouldn't you just add them since square roots cancel?
Not across plus signs. It is never the square root of like 36 plus 25. This is not equal to 6 plus 5. That's not the way square roots work.
But it's square.
Well, this is 6 squared.
Okay.
But I can't get to this guy because square roots don't play nice with plus signs.
So if it was multiplication.
If it were multiplication, you'd be okay. Yeah.
You could cancel
Yes. If it were 6 squared times 5 squared square root, that is equal to 6 times 5. That's true. And if it were x and y here, that would be equal to x and y. But with plus signs, square roots do not cooperate. So let's do some examples. So eventually, conceptually, I wanna be able to give you an angle that's bigger than 90 degrees, like 225 degrees, and have you find sine, cosine, tangent, all that. Okay? But before we get there, I give you a little kind of stepping stone example to just help you get your head around these definitions. In case they were a little wordy, symbol-y, full of symbols. So example. If the point -3, -6 is on the terminal side of the angle theta, find the values of the 6 trig functions of theta. So we know -3, -6 is on the terminal side of theta. I want to find sine theta, cos theta, tan theta, cosecant theta, secant theta, cotangent theta. All right, 6 trig functions. In fact, if you label this x and you label this y, then you can do x squared plus y squared and get r, and you can just use these definitions without any pictures at all. Okay, but I don't like that. I love pictures. Okay, it makes sense when I see a picture. So what I would do is I would actually draw this point. Where does -3, -6 land? Which quadrant? Third quadrant, because you have to go 1, 2, 3 to the left. 1, 2, 3, 4, 5, 6 down. So they're giving you a point down here. And they're saying that's the terminal side of some angle theta. Clearly theta is more than 90 degrees, right? It went past the 90 degrees. So what we're going to do to evaluate our trig functions is think about the terminal side of theta as forming a right triangle with the x-axis. Right? Focus on this guy, which is your reference angle, and then form this right triangle here. Because reference angles are always formed with the x-axis, the right triangles you draw will always be formed with the x-axis. Nothing will ever, when you're doing these trig problems, you'll never form a triangle with the y-axis, ever. If you're doing that, you're probably doing it wrong. Okay? Or at least confusing things. But the only other thing, so what I really need to be able to accomplish sine and cosine and all that, are to know what the side lengths of this triangle are. What is this side length here? How far do you go? What kind of 3?
-3.
That's important. Right? Because once you start going over 90 degrees, you're going to get negative signs in your trig functions. This guy's -6, because that's the y. That's how far you go down. And then for the r, for the hypotenuse, you have to do a little bit of a calculation. Not much, but a little.
3 out of 5.
Is that what you got? 3 out of 5? Let's try. So r is equal to the square root of x squared plus y squared. So r is equal to -3 squared plus -6 squared square root. So r is equal to 9 plus 36 square root. Root 45, or if you simplify, 3 root 5. All right, you guys remember how to simplify roots? Since there's a perfect square underneath, you can take the square root, right? This is times. So you can take the square root of the 9, which is 3, but then leave the 5 underneath. So fairly straightforward calculation using 3 root 5. And then it's business as usual. And once you have the triangle labeled correctly, then you just do sine. Again, if you want to memorize this new definition, that's fine. Y over r. Right, it'll be -6 over 3 root 5. Or if you already have SOHCAHTOA down, you know it's opposite over hypotenuse, so -6 over 3 root 5, either way. Are we going to leave it like this? No. What are we going to do?
Reduce the 3 and the 6.
Rationalize the denominator, right? So we got to get rid of that root 5, and we're going to reduce the 6 and 3. But I was more concerned with this root right here. So I'm going to get rid of the root 5. So it becomes negative 6 root 5 over 15. And then the 6 and the 15 reduce. The 3's in both of them. So it's going to be 2. So 2 root 5, negative 2 root 5 over. I'll do the other one. I'll just stop and ask you if you're with me or against me. One comment. If you do not have this negative sign, you will get no credit. This is the whole reason. This is the whole important part of this new section, right? Otherwise, all we're doing here, besides this negative, all we're doing is opposite over hypotenuse, right? That's right triangle trigonometry. That's the last section we did. That was on the quiz. Right? The whole thing that makes this new and interesting and the answer different is that there's a negative sign. So these negatives are, to me, and therefore to you, super crucial. Pay attention. Cosine theta, you can do x over r, or you can do adjacent over hypotenuse. It's going to be negative 3 over 3 root 5. Reduce and rationalize. Reduce first this time. You'll get negative 1 on top, root 5 on bottom. And then you rationalize by multiplying by root 5 over 3. So negative root 5. What do you think? Easy or hard? Or somewhere in the middle? I don't know. I can't make a decision. Okay. That's fine. I guess it doesn't matter. It is expected that you learn. Tan theta, opposite over adjacent, or y over x. So negative 6 over negative 3. Here the negatives cancel and you actually get a positive answer for tan. And then the other three are just reciprocals, right? Cosecant theta is r over y. Secant theta is the reciprocal of cosine, so r over x. And then cotan theta is x. You could just flip these out. You're going to make yourself a little bit extra work if you flip this guy, because if you flip this final answer for sine, the root comes on the bottom again, and then you have to rationalize again. So either you could go back to the original and just do r over y, that's fine. Or you can flip it where the root's on the bottom, right? So if you flip this guy, that would be a little bit easier, because then you don't have to rationalize again. But either way, you should end up with, if we just go straight back to the triangle, 3 root 5 over negative 6, reduce the 3 and the 6, root 5 over 2. Same thing with secant. If I flip this guy, I'm going to have to rationalize again. So instead, flip the guy that has the root on the bottom, or come back to your original and do r over x. So 3 root 5 over negative 3 is r over x. So the 3 over 3 cancels to 1. You don't even need to write that, but you do need to write the negative. Okay, that comes out in front. Doesn't go away. Cotangent will be negative 3 over negative 6, or 1/2. Yes, sir. What are you
trying to find r and you took the square root of 45,
Yes.
why wouldn't it be negative 3 root 5? Why wouldn't it be positive?
Because r is defined this way. Meaning that if you walk up to somebody on the street and you say, what's the square root of 25? They don't tell you negative 5, right? What do they tell you? Positive 5. Square root of 25 is 5. Everybody knows that. Square root of 36 is 6. So if I define r to be the square root of something, I'm defining it to be positive.
Okay.
If I wanted r to be negative, I would have to do this. Put a negative on it. But the way that we're defining r, all of our signs are kept track of by the x and the y. Okay, the r is always going to be positive. You can think of it kind of like a radius of a circle. See, a lot of times students will get confused because just related to your question. Like if I tell you to solve, there's two kind of problems, well there's one problem you run into with square roots. If I tell you to solve x squared equals 25, versus if I ask you to calculate or evaluate root 25, these are two different things. Okay, and they'll have two different answers. In the top case, if you're solving this equation, you realize, because you're smarter than the equation, you realize that both a negative answer and a positive answer will work here. Both negative 5 squared and positive 5 squared will solve this equation. So when you solve this, we invented something called the square root property, where you just take the square root of both sides, but add a plus or minus. Right, you add that plus or minus in manually. And then you get x equals plus or minus 5. But this is totally different. This is saying I only want the positive square root. And I'm not putting the square root in there with some property, it's already there. So if you just see a square root with no sign out in front, the answer is always positive. So you won't get a negative unless you physically put the square root in. If it's already there in the definition or in the problem, you don't worry about the negative. Okay. So what happened in that problem is I gave you a point, and using that point we got a right triangle. Okay. What we want to do now, that's good. It's good to know. It gets us used to the definition, but it's not that big a deal. All right. But what is a really big deal, what I really want you to be able to do, is take something like sine of 4 pi over 3. Right? Figure out what the exact value of sine of 4 pi over 3 is. Okay, so plug this angle into the sine function and tell me what you get out. So let's work through that. It says use reference angles to find the exact value of sine 4 pi over 3. What we're going to need somewhere in the back of our head to work this example is our special right triangles. All right, so remember from last time we had a 45, let me use radians actually. In radians, 45 degrees is pi over 4, and then this was 1 root 2. So that helps us get our sine and cosine values for pi over 4 angles. And then we also had a pi over 6, or a 30 degree reference, or a 30 degree angle, which had a pi over 3 and a right angle. The sides here were labeled 1, 2 roots. So these are going to come in handy on the next couple examples, so let me leave them up here. All right, so sine, I want to calculate sine of 4 pi over 3. So, because you know how I operate, I want a picture first. Right? Otherwise, my brain just doesn't function. So tell me, where does 4 pi over 3 land? Third quadrant. Why? It's 1 more than 3 pi over 3. Right? 3 pi over 3 lands right here. 3 pi over 3 is the same thing as pi. 4 pi over 3 is 1 more. So if I were going to graph that, I'd take my pi, split it into 3. So 1 pi over 3, 2 pi over 3, 3 pi over 3. But I actually need to go 4 pi over 3. So I split this guy up as well. 4, 5, 6. So then I see that 4 pi over 3 lands down here. This guy from here all the way over here. So I'll draw my right triangle. Right, remember the way the definition works, when you have angles that are bigger than 90, you draw a right triangle with the x-axis. And then the question kind of becomes, first of all, what's this reference angle right here? And why? So what's this leftover portion? Pi over 3. Right? If you ever have an angle that has a denominator of 3, if it doesn't reduce, the reference angle is pi over 3. That's one way. Another way is just look at what happened. We went 1 pi over 3, 2 pi over 3, 3 pi over 3, and then we went an extra pi over 3. So this guy's pi over 3. If this guy's pi over 3, what's this? Not that it really matters, but what's this guy down here?
Pi over 6.
Pi over 6. This is a 30, 60, 90 triangle. Pi over 6. So what I'm going to have to do to evaluate sine of 4 pi over 3 is somehow make reference to this triangle over here. Go ahead.
I hope I asked this correctly.
I'll correct
Say
if you don't.
if it's divided, the pi is divided into 4
Yes.
pieces, and the terminal lands on the y-axis, how do we determine what the reference angle
There is technically not, I mean, reference angles aren't defined when you land on an axis.
Okay.
So there's a different, well, slightly different strategy.
You would never see like 14 pi.
Oh, you will. There's just a slightly different strategy to
Oh, okay.
work with it. And I have an example at the end that I'll go through so you can figure, so you can see.
Okay.
But for now, we're going to deal with things that don't land on an axis. Landing on an axis is a special case.
Okay.
We'll get to that. So what I need to do to actually figure out what sine is label this triangle correctly, right? But when I label the triangle, I'm going to focus on this known triangle right here. So the way that this works, and you got to kind of be careful and make sure you match everything up correctly. Right? Even though, don't scale, not to scale. This is not to scale in any way, shape, or form. Okay? What you want to focus on, for example, is the thing touching the pi over 3 is 1. Right? So over here, the side touching the pi over 3 is going to be 1. So when I label this, I'm going to label this side 1. That's my value, almost. What else do I need?
Negative.
Negative, why? Because it's going in the negative direction, right? So the way we keep track of the fact that this went over 90 is putting a negative in front. Right? The way that we keep track of the fact that we're in the third quadrant is making our x negative. Y will also be negative, right? Because y is going down. But what's my y value? Square root of 3. Y, if you look at the triangle here, whatever's touching the pi over 6, that's root 3. So touching the pi over 6 should be root 3. Positive or negative?
Negative.
Negative because you're going down. And then your r, or your hypotenuse, is 2. R is never negative, ever. Ever, ever, ever.
I'm confused because I thought things were negative if it went opposite of standard position.
Okay, so those are angles, but these are not angles. I'm not referring to angles. Right? The angle that we used was 4 pi over 3, which went like this. Right? But I'm not talking about this angle, this rotation. I'm talking about this side length, like if you were walking along the x-axis and then walking along the y-axis.
Oh,
Like if you're applying points.
Like if you're on a coordinate.
Right, on the coordinate plane. Right? Think of this as the x-axis and y-axis.
So your sides basically determine what, the signs determine the quadrant.
The quadrant determines the sides, the signs determine the determine the quadrant determines the signs, yes. They're
So
one and
2
the same.
is positive because it's a positive slope, right?
No. R is always positive. That's why.
Okay, R is always
R is to find b positive. So then what's sine of 4 pi over 3?
Negative 3.
So for sine, you would do y over r, or opposite over hypotenuse. Opposite of pi over opposite of your reference angle is negative root 3 over 2 for the hypotenuse. Don't forget that negative. That's the whole point of this. So eventually, when we get to the unit circle, which is the next section for the next week, I will give you a very nice way, because there's a lot of, I mean, if you've never seen this or never done this before, there's a lot of information going on here and a lot of connections to be made. When we get to the unit circle, it kind of brings it all together and gives you a nice picture that you can memorize or use to remember all these things. But for now, I really want you to actually understand what's going on. Okay, I actually want you to know where these numbers are coming from, why they're negative, etc. So we're going to, for this section at least, we're going to draw this picture whenever we want to find a trig function of a certain angle. We're going to draw the picture and then label the triangle correctly and find opposite over hypotenuse or whatever we need. But questions? Yes, sir.
Credit, can be expecting us to draw pictures.
Questions of the form for credit, you will be expecting this, are of minimal value to me. I don't know. I mean, you know, because you got to take into consideration the fact that, well, our quizzes are multiple choice, right? So, I mean, really, you could pray to your God and roll a die and flip a coin and get the right answer, and I'll give you credit there. But on a test, if it's like a short answer question, if I want a diagram, I will say, draw the angle or draw a diagram. I'll be very specific about that. So yes, I want it, but if I really want it for credit, I'll put it on. Because some people, you know, some people can get it without the diagram just fine. Right? Some people don't think that. So I'm not. Certainly the diagram's helpful. And if it's a short answer, the diagram will get you partial credits. All right, let's do another one. Let's do it. Cosine of 315 degrees. Ooh, yeah. It's in degrees. That's easy. Things in degrees are easier. Where's 315 degrees land? All right, that's our start. If we want to evaluate cos 315, we got to figure out where this lands. Fourth quadrant. In fact, how far is it from 360?
45.
45 degrees. This is exactly 45 degrees from 360. So I know my reference angle here is 45 degrees. This angle, right, the angle that I actually graphed here, that's 315. But as far as all of my calculations are concerned, I care about the reference. So I go ahead and draw my triangle with the x-axis always. Because it's 45 degrees, I know I have a 45, 45 right triangle. So I know I'm dealing with this schematic. I label the side lengths 1, 1, root 2. That'll work, but you got to have your signs right. S-I-G-N-S. I didn't want you to get confused with S-I-G. So, will this 1 be positive or negative?
Positive.
Positive, because you're going the positive x direction. What about this one here? Negative, because you're going down. And what about the root 2?
Positive.
Always positive. So cosine of 315 is adjacent over hypotenuse, which is 1, right? Adjacent refers to the reference angle. So adjacent is 1 over root 2, which is not exactly an acceptable format. So you rationalize, just like you rationalize away your problems in life. Root 2 over 2 will be your end result. positive. Right? Even though we had a negative here, my cosine still ended up being positive because the negative was not on the adjacent side. It wasn't on the x. This guy?
Yeah.
Right? Because it's all. Never ever. All right. One more, two more. I'll just do one or two more. All right, we'll run through these quick. So I gave you some angles that are actually more than one revolution. That might trip you up. So example, I want you to be able to evaluate, for example, tangent of 870. What's your strategy? How does this work?
It's going to be 2 revolutions.
Yeah, you got to graph it first, right? And when you're graphing this, you're thinking 870 degrees. That's a lot of degrees. Cool. It's more than 360. It's more than 720, right? 720 is 2 revolutions. In fact, it's 150 more than 720. Right? So somewhere in your head, you want to be thinking that this guy is 720 and then another 150. And yes, 150 will end up in the second quadrant when you graph it. So we'll go 360, 720, 90, right? And then another 60 degrees. So this guy, we did 360, then we did 720, that was our second revolution, and then we did an extra 150. So this portion right here is that extra 150. Okay, super bueno. What actually matters when we're figuring out our trig functions is the reference angle. Right? So this reference angle is going to be what?
30 degrees.
30 degrees. Because we went 150, and to get back to the x-axis is 180. So there's 30 degrees left. We draw our right triangle with the x-axis always. We label it according to this guy, right? Pi over 6 is 30 degrees. This is 60 degrees. So we know it's 1, 2, root 3. 1 is across from the 30, so like this. Be careful. Mess that up for you. Right. Root 3 is across from the pi over from the 60. Or root 3 is touching the 30. So make sure you orient your numbers correctly. And then you got to account for the signs. So let's start with this 1 here. Is this 1, should it be positive or negative? Because you're going up, it's positive, right? Y going up is positive. Root 3, from the origin, you're going to the left. So root 3 should be negative. 2 is the hypotenuse, always positive. So, my scholarly chums, tangent of 870. Total opposite over adjacent. 1 over root 3, negative.
Negative root 3 over.
Yeah, so if you just evaluate directly from the triangle, you'll get 1 over negative root 3, which is all well and good, but kind of ugly. So we'll go ahead and rationalize. So the root 3 times root 3 becomes 3. All right, that's your last one. So your root 3 becomes 3 on the bottom, and then you get a root 3 on top, so negative root 3 over. How's that feel? Oh, these guys, yeah, they rock out all the time. They're always rocking out. They're always watching videos. That class is so much fun.
I bet they're not having as much fun as us.
Oh, no way, man. So one more. Use reference angles to find secant of negative 31 pi over 6. So you got to graph it. Gots to graph it. So 31 pi over 6, I would probably convert that to a mixed number. Right, so 6 goes into 31 5 times with a remainder of 1. So this will be negative 5 and 1/6 pi. As far as graphing goes. That's the angle we want. And the negative does matter because you'll end up in the wrong quadrant if you don't take that into consideration. So when I go negative 5, right, so first I'm going to do my negative 5 pi. Here's negative 1 pi is half revolution, negative 2 pi, negative 3 pi, negative 4 pi, negative 5 pi. Lands me right here. But then I also have to go an extra pi over 6. So I break my top pi into 6 equal sectors. 1, 2, 3, 4, 5, 6. So this is about where all. What's my reference angle? For 6. Right, because we went negative 5 pi, and then we went 1 pi over 6 after that. So that little bit extra will be your reference angle. Then you draw your triangle. And you'll notice, hopefully, maybe, it's actually the same exact triangle as we just had here. Because we landed in the same exact place. Even though it's a different angle, right? Because we went around, we went in the negative direction instead of the positive direction. It's technically a different angle, but it doesn't matter. If we land in the same place, the trig function is going to give us all the same stuff. But we got to label it. I'll go ahead and label it the same, and hopefully that makes sense, right? This is 1, this is root 3, this is 2, and then the root 3 will be negative again because we're in the second quadrant, and x is negative. So then when I evaluate secant, what am I looking for? Secant's the reciprocal of cosine, right? Secant and cosine. So cosine, so cosine is adjacent over hypotenuse, which means secant should be the other way, hypotenuse over adjacent. So on my picture here, I'm going to take the hypotenuse and divide it by the adjacent. Or r over x, like that. So I'll take 2 and divide it by negative root 3. Which, I don't know, I'm superficial, that's ugly, I hate it. So I'm going to change it and make it be more like something I like. 2 root 3 over 3. Wait, is that right? 2 root 3 over 3? Circle it, done? Oh God, you're missing a negative, right? This is terrible. This failed life. There you go, now you pass life. What do you think? We're getting this down? If I give you sine, cosine, tangent of some angle, you can do this maybe? See? We'll see next week. There's one more thing that we have to cover. I have 2 examples, 3 examples. I won't get to all of them, but I'll get to one of them so you see what I'm talking about. Actually, while I have this up here, let me skip to the last example. Because it's more similar to this, and then I'll go back to the other, I'll do one of the other 2. But the last example is about the question that was asked earlier, if you land on an axis. Okay, so let's talk about when you land on an axis. So let's find sine of pi over 2 and cosine of pi over 2. you remember, the way our definitions work for angles that were 90 or bigger, for non-acute angles, the definitions were all set up with a point. Right? It actually you didn't have to have a triangle. We just made a triangle because it made sense to me. But really, sine of theta has this definition that has nothing to do with a triangle, y over r. And cosine of theta is x over r. That's our definition. And we can apply that in this situation, even though we land on the y-axis. Right, our angle here is pi over 2, and hopefully you understand, since this is pi, if you cut it in half, you'll be landing up here. So this is pi over 2. Now we don't actually have a triangle we can draw for this. Because there's no acute angle we can make with the x-axis, because on both sides it's 90 degrees. So what you do is just use your definitions. You pick some point on this ray. I don't care, any point on this ray. Pick an x and a y value that's on the y-axis. Like, can I pick 2, 7? Is 2, 7 on the y-axis? No, if you go over 2, 7. What is on the y-axis? 0, 5. That's a good one. I love that one. That's the one I would pick. Right? It has to be 0 though, right? So that you don't go left or right, then you go up 5. And this number doesn't matter. 0, 10, 0, 100, 0, 1. I probably would have 0, 1 actually, sorry. But now we can do our definitions. Sine of pi over 2 is equal to y over r, which is equal to 5 over r. What's r in this case? R is forever and always the square root of x squared plus y squared, which if we plug in our values, 0 squared plus 5 squared square root, square root of 25 is 5. So r happens to be the same as 1. Sine of pi over 2 is 1. You see how it doesn't matter which number you put here? Like if you put 10 here, then y would be 10, but you would do 0 squared plus 10 squared, and when you square root, you would get 10 for r. So r and y will always match for this point. So then what's cosine of pi over 2? X over r, right? Cosine of pi over 2 is x over r, which is equal to 0 over 5, which is So, can we evaluate trig functions on the axes? Yes, we just have to pick any point on it. Okay? Really, this is making it overly complicated. When we get into 6.2 and we go back and do the unit circle, this will become abundantly obvious. Right? Probably the easiest thing to do is evaluate trig functions on the axes.
What section?
This is 6.2.
Oh.
Yeah, so we're gonna go back next. Let me do one more example and then I'll let you go. So what I'll do is I'll run through this example quickly and then I'll go over this again as review on Monday. Okay? But the last thing that's in this section, the last thing we want to be able to do is if I give you one trig function, right, you want to be able to find the values of the remaining 5 trig functions. Let me show you this example. Sine of theta is negative 12 over 13. And theta is in quadrant 3. The question says find the values of the 5 remaining trig functions of theta. in my head, what's going on is I need a picture. Right? If I could just get a picture for this, it'd be easy. So that's what I'm going to do. Theta's in quadrant 3. This is quadrant 3. So there's theta. Now, I have to be a little creative because I don't actually have a measure of theta. I don't know what theta is. But I do know that sine of theta is negative 12 over 13. So what you want to do is kind of imagine a right triangle in here. And use the fact that sine of theta, which I know is opposite over hypotenuse, is equal to negative 12 over 13. Use that fact to label this right triangle. Meaning match up opposite with 12 and match up hypotenuse with 13. And then we'll worry about this next. So in order for sine to be 12 over 13, I can make this opposite side 12 and this hypotenuse 13, and then sine will be 12 over 13. But I need it to be negative. How do I fix up for that negative? The negative has to be 12. Why isn't the negative on the 13?
R is never.
R is negative negative. R is never negative.
So theta is automatically in the corner closest to where.
Right, so this has to do with the idea of reference angles. When you draw this right triangle, you draw it with reference angle as its acute
Oh
angle.
yeah, from the x-axis.
From the x-axis, yes, yes, yes. That's why I said if you're ever doing things with the y-axis, wrong. Almost always we use the x-axis. So now can you find this last side? How? Pythagorean theorem, right? X squared plus negative 12 squared equals 13 squared. Do it all out, you should get x equals 5. Yeah, you got to be careful with the sign here. You don't want to put positive 5 here, why not? It's going this way. You're in the third quadrant. Right? So even though when you solve this, remember the way the solution, the way you actually solve this, you get x squared plus 144 equals 169. You subtract the 144 over, x squared equals 25. Now, because we're square rooting both sides, because we are introducing this ourselves, there are two choices. And what I'm saying is, I don't want the positive because I'm in the third quadrant. So it's more like a puzzle. You start with a couple pieces of information, and then you fill in the rest, and now you can read off all of your trig functions because you've got your triangle label. Right? Cosine of theta, for example, would be negative 5 over 13 because that's adjacent over hypotenuse. Tangent of theta would be what?
Negative 5. Oh,
Opposite over adjacent.
Negative 12.
So negative 12 over negative 5, which is actually, yeah. Sine I already have, so then I just do my 3 reciprocal functions, which I'll leave for you to do. So I will, this is in 6.3. Definitely start your 6.3 homework. You should be able to do all of it if you can. Ask me on Monday. And I will go over one more of these on Monday to make sure we got it.